I am Mr. Alan Maestri. I am your Calc 2 instructor for the term. My contact information is on the board. Please review the syllabus when you get a chance. Your grade in this class is based on 3 tests, 6 required web-assigned homework assignments. As of today, you should be able to pay for and access Cengage, the ebook, and web-assigned homework. The ebook, of course, includes examples and additional practice problems, as well as the web-assigned homework. You should be able to access that directly through Blackboard through the textbooks tab as of today. So please, there's a tech support link if you need it, and if that doesn't work for you, please contact me, okay? 3 tests, 6 homework assignments, 2 Maple assignments. You can either use the cloud version of Maple or you can go to the CS Mott building. There's a computer lab, first come, first serve. Those will be announced well in advance, and the final exam. Okay, that's what your grade is based on. Attendance at every class is expected. I can tell you, first of all, that the first test date is Tuesday, July 29th. That's 2 weeks from tomorrow. Please read through the final exam policy and let me know if you have any questions, but here are the highlights. First of all, taking the final exam, sitting for it, and at least making a reasonable effort is absolutely mandatory for all students. Regardless of your grade going in, regardless of your point total going into the final, every student, every one of you is required to sit for the final exam and make a realistic attempt. If you take all 3 tests, okay, test 1, test 2, test 3, and the lowest of those 3, okay, I will look at the lowest of those 3. If your final exam percentage is higher than the lowest of your 3 test scores, I will go back and replace the lowest of your 3 test scores with your final exam percentage, okay? If you miss one of the 3 tests, I will go back and replace the missed test with your final exam percentage, okay? Under no circumstances will the final exam be waived. Will your grade be increased in any way? Will it be made to worth less than the 150 points in any way? Okay, so think about that. If you have questions, let me know. All right, let us begin. This class, of course, is Calculus 2. Now, you just spent Calculus 1 talking about differentiation. First, you talked about limits and continuity, and then differentiation, taking a derivative, right? You learned how to find, well, first of all, you learned situations where a function was not differentiable, where the derivative did not exist. You learned how to find the derivative of polynomial functions, powers of x, rational functions, quotients and products of functions, compositions of functions, right? The chain rule, trig and inverse trig function, exponential and logarithmic functions, okay? And you also did some applied problems such as those involving related rates and optimization, right? Okay, so you all know, for instance, that the derivative of x cubed is what? 3x squared, and you all know how to find it, right? In other words, we're taking the derivative with respect to x, that's important, right? Of x to the 3rd power, okay? So the power of 3, we bring that down as a multiplier, times x, and then what do we do with the exponent? We drop it by 1, right? And of course, you know that, first of all, there are multiple notations, okay? We could say that f of x equals x cubed, which would mean that f prime of x, right? The f prime of x, the derivative of f with respect to x equals 3x squared, right? We could also say that y equals x cubed, whereupon dy dx, right, the derivative of y with respect to x equals 3x squared, or if we're really pressed for time or space, we can even say y prime equals 3x squared, although y prime does not mention the variable with respect to which we're differentiating, right? So there's multiple notations we can use. And of course, you understand the chain rule application of this. Let's just say that instead of finding the derivative of x to the third, let's say we want to find the derivative of x squared plus cosine x to the third power. What would we do then? Okay.
Minus cosine, right?
Okay, it would still be, we have the power of 3, so we would still bring the 3 down as a multiplier, right?
Negative sine.
And then x squared plus cosine x, we wouldn't change that at all, right? Just like we didn't change the x here, right? And we once again, okay, knock the power down by 1, but this time we multiply by what? The derivative, right? 2x minus sine x. Right, remember when you're differentiating cosine x, it's negative sine x. Differentiating sine x, it's cosine x, right? Okay. Every mathematical operation you've learned about, eventually you've learned about its inverse. The inverse of addition is subtraction. The inverse of multiplication is division. The inverse of exponentiation is taking a log, etc., right? Well, the inverse of differentiation is anti-differentiation. And notice the symbolism, okay? The derivative of x to the third equals 3x squared. Therefore, the antiderivative, note the symbol. It's called an integral sign for reasons we'll talk about later. The antiderivative of 3x squared dx. Notice that when you take a derivative, the dx or dt or what have you is in the denominator. When you integrate or take an antiderivative, it's in the numerator, right? Well, since the derivative of x cubed is 3x squared, it only makes sense that the antiderivative of 3x squared is what? X cubed. Okay? Now, is x cubed the only answer? Okay. The general antiderivative, okay? In other words, x cubed makes sense because the derivative of x cubed is 3x squared, right? What about x cubed plus 5? That also has a derivative of 3x squared, right? X cubed minus 2, x cubed plus any constant, right? So the general antiderivative of 3x squared with respect to x, we write as x cubed plus c, where capital C stands for an arbitrary constant. You could put any real number in for c, okay? This is the general antiderivative. This is the family of functions with derivative 3x squared. Is that clear? Make sense? Okay. Are there, very important question, are there any other functions other than functions of this form that have a derivative of 3x squared? And how do we know that there are or aren't? Which is it? How do we know that there are not? Okay? Did you study the mean value theorem in Calc 1? Some of you maybe did, some of you didn't. Okay? Very quickly, the mean value theorem deserves a diagram. you are given that f of x, okay, this is the graph of f of x, is continuous over a closed interval. Okay, do you agree from looking at this graph that this function is continuous on the closed interval from a to b, right? And it also has to be differentiable at every single point on the open interval from a to b, okay? If a function meets these conditions, okay, let's draw the secant line. You know what a tangent line is, you know what a secant line is. I hope finding the equations of tangent lines was part of what you did in Calc 1. By the way, once you find the equation of the tangent line and write it in point slope form, how do you write the equation of the normal line? And what is the normal line? What is the normal line with respect to the tangent line?
The antiderivative?
Perpendicular.
Oh.
So it's going to pass through the same point, right? But how will its slope compare to the slope of the tangent line? Two lines are perpendicular if one is vertical and the other is horizontal, or what?
Their slopes are inverse?
Their slopes are, be a little more precise, negative reciprocals of each other, right? 3/4, negative 4/3, right? -5, positive 1/5, right? Okay. So you can all visualize what a tangent line is. At that, in the immediate neighborhood around that point, the curve and the line have the same slope, right? Okay, a secant line, in contrast, passes through 2 points. So we've got 2 points here. We've got A, f of A, and we've got B, f of B, okay? So there's the secant line through those 2 points. Nothing to do with the trigonometric secant or tangent. It's just what it's called. The mean value theorem states that if a function meets these conditions, then there exists a value of x, okay, where C lies in the open interval between A and B such that, and okay, S period T period stands for such that, okay, such that the derivative of f at that point equals the slope of the secant line. For example, and such a point might be right there, okay? The slope of the tangent line at C, f prime of C, equals the slope of the mean value theorem says that if these conditions are met, you can always find a point in the open interval for which that is true, right? The mean value theorem implies that if the derivative of a function is positive on an interval, the function is increasing on that interval. Negative, it's decreasing. 0, and the function is constant on an interval, which leads directly to the fact that if two functions have the same derivative on an interval, then they differ at most only by a constant. Is that clear? So the question can be raised, are there any other functions other than functions of this form? And the mean value theorem gives us a firm answer to that question. No, there are not. Okay? All right. Let's look back at how we took the derivative of x to a power. We used the power rule, right? In other words, now think about this, because it's a two-step process. First of all, we multiplied by the exponent, right? We multiplied by 3, and then we reduced the exponent by 1, right? Those are the two steps in that order. Now, clearly we can see how we got there, but if we didn't, if I just said what's an antiderivative, or what's the general antiderivative of 3x squared, what would you do? You would do the reverse steps in the reverse order, right? Okay, so the first thing, now the last thing we did here was knock down the power by 1. So what do you think the first thing is we do when we anti-differentiate?
Increase the power.
We increase the power by 1, and then we divide by the new power. Good, right? Which of course is x to the third. Do we already have a general rule to find a general antiderivative of x to a power? I think we do. By the way, I uploaded 3 documents into week 1. Please review them when you get a chance. One is a 6-page synopsis. It doesn't replace the ebook, but it's intended as a supplement, as a distillation of what's in the ebook. Okay, 6 pages of notes for the sections we're covering for test 1, 4.9 through 6.1. 1 page of 16 basic antiderivatives. You will be allowed to use that on the test. On test 1, I can't vouch for future tests. However, it should be pretty clear that the more of that table you know by heart, the better off you'll be, if for no reason other than you won't have to constantly be glancing at the table, right? You're better off knowing them by heart, but you will have access to the table. And then finally, a test 1 review packet that we will work through when it's time. All right. So, the antiderivative, the general antiderivative of x to the n dx, okay, what's the first thing we do? Bump up the power by 1. Second thing, divide by the new power. And we have a general rule. Now, does this formula work for every real n? Or is there one exception? Yes.
Would the one exception be with trig?
Okay. This function, let me just, okay. This formula works for any x and for any real value of n except for -1, right? Because if n is -1, -1 plus 1 is 0. You can't divide by 0, right? Okay. Fortunately, so this works provided that n does not equal -1, right? I'm gonna have to repan the camera here. Okay, can everyone see okay from where I'm writing on the board? Okay, so that's the one. That's the one exception. Now, if n equals -1, in other words, if we're taking the derivative of x to the -1 dx, which we can also write as the antiderivative of 1 over x dx, or even, and this is how we usually write it in fact, dx over x. Does anyone know what that is? It's the natural log of the absolute value of x plus c. You need the absolute value. You can only take the log of a positive number. So this covers the case where x is negative as well. So we have a formula for if the power is -1 and a formula for all the others. Is that clear? Okay, many of you after this class will be taking Calculus 3 and then differential equations. You may find this hard to believe, but you are already at a point where you can solve some very, very, very simple differential equations. What do you think? find f of x such that, you might as well get used to this abbreviation, such that, in your math classes, because you'll see it all the time. Find f of x such that, and I'm going to give you two conditions. The first is that f prime of x is 2x plus 3. And the second is that f of 2 equals 1. Okay? Now, categorically, what this is a differential equation. Why is it a differential equation? Because it's an equation with a derivative in it. Okay? It's an extremely simple differential equation, but it is a differential equation with a boundary condition. I'm giving you that when x is 2, f of 2 is 1. Boundary condition is also sometimes called an initial condition. Okay? We solve the differential part first. Okay? In other words, we anti-differentiate. Notice that we're anti-differentiating. You're given the derivative of x, and you're asked to find x. I'm sorry, f of x, right? Let's try that again. You're given the derivative of f of x, right? F prime of x, and you're asked to find f of x. Whereas what you're accustomed to doing is you're given f of x, and you need to find f prime of x. So we're going the other direction. Okay? Fortunately, we know how to do that with this type of expression. The antiderivative, the general antiderivative of 2x plus 3 dx is, and antidifferentiation is like differentiation. It is a linear operator. We can go term by term. What do we mean by a linear operator? Anyone? What do we mean when we say that antidifferentiation, like differentiation, like finding a limit, is a linear operator? What do we mean by that? Here's what we mean. Let's go back to differentiation. You should know what a linear operator is. Okay? Differentiation, taking a derivative of a function, is a linear operator because the derivative of a linear combination of two functions, a times f of x plus b times g of x, where f and g are differentiable functions and a and b are any real numbers, equals a times the derivative of f prime plus b times the derivative of g. That's what it means to say that differentiation is a linear operator. So is anti-differentiation. Is it clear what a linear operator is? You should at least be familiar with the idea. Quick question, is squaring a number, or let's say not a number, let's say is squaring an expression a linear operator, yes or no? Yes or no? Who says yes? Who says no? Why not?
Because it keeps double, or I get double.
What was a great way in middle school or high school to annoy your algebra teacher? Right? Is that true? Yeah. Yuck. Algebra teachers hate when students do that. I know, because I was one. Anyway, squaring is not a linear operator. X plus y squared does not equal x squared plus y squared like it would if squaring were a linear operator. So squaring is not a linear operator. Taking a derivative is. Taking an antiderivative is. I want you to at least be familiar with the concept of a linear operator and a linear combination. All right, now having said that, the point is, the antiderivative of an expression like 2x plus 3 is simply the antiderivative of 2x plus the antiderivative of 3, plus an arbitrary constant, right? All right, so let's use, I don't guess we need to use this rule unless we have a 1 over x in the expression, right? And we don't. So let's use this rule. Antiderivative of 2x. Follow the procedure. 2x squared, and then what do we divide by? The new power, so that just becomes x squared, right? Okay. And then what power is x being raised to in this expression? 3.
1.
The 0 power, right? Here it's being raised to the first power, x to the first. Here x is being raised to the 0 power, right? X to the 0, we can treat that as 1, okay? So we bump up from 0 to 1, then divide by the new power 1, well that's just 3x, right? Which makes sense because what's the derivative of x squared?
2x plus
2x, and what's the derivative of 3x? Okay, plus an arbitrary constant. Are there any questions about that? All right. We were asked to find f of x given 2 conditions. If the only condition we were given was this first one, we'd be done, okay? What we have here is the general antiderivative of 2x plus 3, okay? Since we're given a boundary condition, we need to find the one function that meets this condition, which we just found the family of functions that does, and that meets this condition. How do we find the one function in this family of functions that also meets that condition? Yes.
You could plug in x to be 2 and set the entire equation equal to your value.
Excellent. Okay, f of x is what we're trying to find. F of 2, okay, this is f of x, right? Any constant will make this, right? But now we need f of 2, so that's going to be 2 squared. Everywhere you see an x, you replace it with the 2. Excuse me. 3 times 2 plus c, and we set that equal to its value, which is 1, and we solve for c. Is that clear? 2 squared is 4. 3 times 2 is 6. 4 plus 6 is 10. And when we subtract 10 from each side, it's pretty clear that c equals -9. However, don't just circle that and be done. Write the function. F of x equals x squared plus 3x minus 9. This is the only function. There are many functions that meet the first condition, any arbitrary value of c. There are many functions that meet the second condition. F of 2 equals 1. X squared minus 3, x minus 1. There's a bunch of functions that, right? X over 2, there are many functions that, such that f of 2 is 1. But there is only one function that meets both these conditions, and it's right there. Exactly. Okay. Later on, we will discuss both indefinite integration, which is the same thing as what we've been doing, general antidifferentiation, and something called definite integration, which is where you have lower and upper limits, okay? But I'm just going to introduce you to the topic by way of pointing out that, let's see, kind of up here, we'll go over here, that there is a relationship between differentiability, continuity, and integrability. Okay? You may recall from Calc 1 that differentiability, and I'm abbreviating, implies continuity. If a function is differentiable on an interval, then it's continuous on an interval. However, the converse, you all know what a converse is not necessarily true. In other words, continuity does not necessarily imply differentiability. Who can give an example of a function that is continuous on an interval but has at least one point where it's not differentiable? Anyone? Yes.
Absolute value of x.
The absolute value function. Very good. Okay. So y equals, by the way, is the absolute value function a piecewise function? Sure is. The absolute value of x is defined to be x if x is greater than or equal to 0, and the opposite of x if x is less than 0. That's a piecewise definition, right? And of course, it has the familiar V-shaped graph. Continuous. You can draw the absolute value function in one continuous motion, but the slope of the tangent line abruptly changes. Okay, so we're graphing y here. So if we graph y prime for any negative x, okay, dy dx, for any negative x, the slope is -1, right? But then at 0, it abruptly changes to +1, right? So the absolute value function is not differentiable at 0, is it? But it's still continuous. Likewise, if a function is continuous, then it is integrable. However, there are a few, not many, but there are a few functions that are integrable that are not continuous, and one of them you should be familiar with. It's called the greatest integer function. Are you familiar with it? It is a step function. Let's say y equals int x. It's also sometimes called the floor function and denoted like that. Okay? Let's say x equals -2. The greatest integer function is the greatest integer that is less than or equal to x. So the greatest integer function of -2 is -2. As x increases, the greatest integer function remains -2 through just before we get to x equals -1, and as soon as we reach x equals -1, what happens? It jumps up to -1, and so on and so forth, right? Forever and ever and ever. Okay? Three, and then let's go up to 4. Okay? Is that clear? So it's a step function. Now, we're going to elaborate on this, but one of the physical representations of a definite integral is the area under a curve. Okay? So, first of all, can we all agree that the greatest integer function is not continuous? Okay, now. If you were to ask a small child to find the area under the curve, okay, between x equals 1 and x equals 4, note the notation, what would she or he do?
Count the squares.
Count the squares, right? The integral of the greatest integer function from 1 to 4 is indeed 6. You can integrate the greatest integer function even though it's not continuous, and there are a few other functions like that. But if a function is continuous, it is integrable. However, oftentimes, in fact, I'm even going to say most of the time, you cannot express the antiderivative of a function in terms of functions that you're familiar with. Okay? Unlike a derivative where you can. All right. I think this is a good place for me to stop my lecture for today, but what I'd like you to do between now and tomorrow's class, okay, I want you to read through the notes that I posted from the bottom of page 1, the section called 4.9 linear motion, where we talk about acceleration, velocity, and position, okay? And then section 5.1 where there's 2 examples. So read through the top of page 3. If you could do that between now and tomorrow. And if you could at least take a look at the table of basic antiderivative just so that you know that it's there. Obviously stay if you have any additional questions. Otherwise, I will see you tomorrow.